Okay. Who here remembers the product rule from derivatives? One person? Come on. I got a couple. Okay, well, good. All right, sweet. Okay, so I'm going to write down the product rule for you again. Should look familiar. I'm going to write it using Leibniz notation. Okay, so not the like we did with notation, but all the dy, dx, and that sort of thing, which you guys are kind of used to now because we've been doing it. So looks something like this. U and v are two differentiable functions. Okay? I'm not writing them in function notation, but we're assuming that to begin with. And I want to do the derivative of the product of those two, right? d dx of u times v. Okay, and what we said was, okay, you would multiply that by the derivative of v, which would be v dx then. Times the derivative of u dx. Make sense so far? Look familiar? We're engaging prior learned knowledge. Get a question? Yeah, that's fine. Okay, so what to do is we're going to do a little bit of integrating here on this thing to come up with a new formula for you, which is this whole integration by parts thing. So if we have a different functions in the mix, it's how we can do an integral for that. Okay, so I'm going to do a little bit of rearranging here at the same time, but see if you can follow what I'm doing. Of u du. Get that all on there. Okay, so everybody follow what I did there exactly? I essentially I applied an integral to everything, okay? Which is okay. It's keeping that equation still in balance then. Okay, the integral of one side is equal to the integral of the other side as long as I do it to everything. And then all I did is I subtracted the one term back over then. Okay, so I took the integral of this last piece here and I subtracted it over to there. And so now I've got this by itself here in integral form is equal to this integral of that one. Okay, so that's the rearranging that I did. Now if you notice, differentials in there, there's some dx's that are going to cancel each other out. Okay, so what we got here then is because those are going to cancel each other out equals, and then I have an integral and a derivative that essentially are going to undo each other. So this is the integral of a derivative, so it's just gone. And this last one, kind of like the first one, the dx's are going to cancel each other. So I've got the integral of v times du. So I've got this formula. You're probably like, great. So now he's showing us a way that we can do the integral of something that's a product of two things, one of which is a derivative, is equal to this product minus another integral. So if I want to do this integral, I got to figure out how to fit this together, and then not only that, then when I get to this stage, I got to have an integral over here that I can do. Yeah. Yep, that's pretty much it. So now, instead of a u with what you have, you're going to choose a u and a dv. Okay, because this is our starting point right here. So you're going to have some kind of a formula in front of you, and you have to decide what's the u, what's the dv, So then when you go through and you find the v and the du and all of that, you can plug it into this so that this integral over here is doable. Because trying to do it directly from here is not going to be doable if you have to use parts to do it. So what your hope is that by breaking it all down, figuring everything else out, that this one down here is going to be a nice simple one that you can take care of. Okay? Give you an example. So let's say we've got okay. Now choosing a u and a dv, that's going to be a skill that we're going to develop here a little bit. So for this first one, though, I'm just going to show you, I'm just going to tell you what we want them to be so you can see how the process works. But as we do more examples, I'm going to go to you guys a little bit more and ask you, okay, so now that you've seen a couple, what do you think? What would be a good choice for each one? But this one, I'm just going to want the u. And it is important that that dx come along. Okay? Because this is a derivative, dv. And when you do a derivative, you should have a dx attached to it as well. So that's how we're breaking this apart. Okay? Now, if you look up here in the formula, I need to know u, v, and du to get into this formula right here. Okay? So I've got u. I need a du from that, though. So I'm just going to go right underneath it, get things organized. What is du? It's 1. Okay? But it's a derivative, so it's 1 dx. Okay? Or just dx, right? So du equals dx. And then over here, I need v. I got dv, though. So what do I need to do to find v if I know dv? Antiderivative, right? Okay? So if dv is cosine x, what's just v? Sine x, right? Integration by parts, you need to have this kind of little table. Okay? Where you have u, du, dv, and v all there. Okay? All 4 of those are going to come into play. My formula, this should be equal to u times v, x sine x minus the integral of v du. v du. So sine x dx. Now, like I said before, my goal was to rewrite this thing in such that the integral on the end is going to be one that I can do. Because x cosine x, doing that direct, we can't do that. But by using integration by parts, I know it's equal to this. And can you do this? Everybody say yes. Yes, you can, right? What is the antiderivative of sine x? Negative cosine. Okay. Sine x, though, that's still there. Because this was a minus. So minus negative cosine through integration. This on what are you going to choose as your u and what's the dv? It has to be 2 things that original integral. One of them is going to be your u, one of them is going to be your dv. And if you pick them correctly, then everything kind of falls into place for the rest of it. And you end up with an integral on the end there that you can do and evaluate, and then you can get an answer. Okay? 1, 2. Let's do... Okay, so this one, oh, that's kind of similar to the last one. Let's just do it. Okay. You guys can probably guess at the on this one without too much. So what do you think? Mm-hmm. And the DV? Yep. You want to, yeah, so if you take your U and your DV and multiply them together, it should be the whole thing that you started with. So, yeah, so if you're going to pick 2t as your U, the rest of it has to be DV then. Okay, but this is workable. We can do this. So, du. Don't overthink it. Do 2 dt. Good. Now the v, we have to do the antiderivative of cosine 3t. Okay, now you might look at that and be like, oh, that's a u substitution, right? It's got a 3t in there. Maybe you guys can do that in your head at this point because it's kind of a simple u sub. I don't know. But then I'd have to multiply that by something. 1/3, yeah. So if we make it a 1/3 in front like that. Oh, and then we don't need the dt. Should be just that. 1/3 sine 3. If you work it back, if you're ever not sure of your v, just take the derivative of it and see if you end up back where you started. So 1/3 sine 3t, that'd be a cosine 3t, but then because of the chain rule, I got to multiply by 3. That cancels the 1/3. Yeah, we're good. All right. What am I going to have forward then on this one? That first term. What do I have to multiply together there? U and v. Okay, so find u, find v. Multiply those guys together. So something kind of like that once you combine things together, right? 2/3 t times sine of 3t. And then I have to subtract the integral of v du. So v and du, well, this has got a constant on it, right? 1/3, and then the du is a 2, so I could take a 2/3 and bring it out front there, and then that'd just be the sine 3t left over. Okay, so again, that integral that we got on the end there, can we do the antiderivative of sine 3t? Mm-hmm. Again, it's technically a u substitution there, but you can kind of think it through in your head probably if you got the other one. So and what would be the antiderivative of sine 3t? Yeah. Get 1/3 cosine 3t. And then don't forget your plus c, and then we'll just do a little bit of distributing here. So 2/3 t sine 3t plus, I guess that would make 2/9 cosine 3t plus c. There you go. All right. Sometimes, and we hate when this happens, but it happens, sometimes you have to use repeated uses of integration by parts. So maybe that integral that you get on the end didn't work, or it's not to a point yet where you can evaluate it yet, but if you were to do integration by parts on that integral, then it's enough where it would work. Okay? So I'll show you one like that. Let's say we've got the integral of x squared e to the x. Right? We choose dv. We want to choose a u in general. So now that we've had a couple of these, let's talk a little bit about this. So deciding what's a u and what's a dv. Okay? You want to try and make things simpler as you go through this, right? Not more complex. So when you choose a u, you're going to take a derivative of it, right? To get your du, you're going to want, when you take a derivative, for that thing to simplify a little bit. And the same thing with your dv, you're going to have to do an antiderivative of dv, so you're going to want something that would simplify when you do that. Okay? So let's think about this for a second. So if I chose squared, and I took its derivative, does it make it simpler? What's the derivative of x squared? 2x. That's simpler, right? Okay, so that might be a good choice. If I chose u as e to the x, what's the derivative? E to the x. Did that make it any simpler? No. Okay. On the flip side of that, if my dv were x squared, would that make things simpler? Doing the antiderivative of x squared be 1/3 x cubed? Not really. But if my dv were e to the x, does that make it any simpler? It would still be e to the x, right? Okay, so there's one of those that's going to just stay e to the x, no matter how we do it, right? But there's only one combination of those two things where something is going to get a little easier to work with. So we want to do u as x squared and dv as e to the x. Okay, because of that. Think about, okay, what's going to make it the wrong way, and you got to go back and try it again and do it the other way. Just this route. Just e to the x. Hey. No problem. So now, if we plug all this stuff back into our formula, it's going to be u times v, right? So x squared e to the x. And then minus the integral of v du, okay? So that would be 2x e to the x dx. I'm just putting the 2x in the front there, but it doesn't really matter. Okay. Well, technically, integral x e to the x. Can you do x to the x, the antiderivative of that? You can't. So guess what? We're going to repeat this process for that. Just that little chunk of it. Okay. E to the x. Do this whole process over. So what's the u, what's the dv, and all that? So what's our u? X. Well, u v x should be x. X. Can I do the integral of e to the x? Absolutely. This would be e to the x minus the x. Now, here's this is that little integral, so I need to take my answer and plug it back in up there, right? I got to substitute that back in where that other integral sat, that whole thing. So final answer here then is going to be x squared e to the x minus, don't forget the 2, and then this, right? X e to the x minus e to the x plus c. Okay, so what do we got? X squared e to the x minus 2x e to the x plus 2 e to the x. And then technically minus 2c, but c is a constant, 2c is a constant. So constant's a constant, just it's still plus c, it doesn't matter. Right. But, okay, sometimes we got to repeat the process. Now this is a pain in the butt, right? Don't want to have to do this. There's a way around it, okay? If you don't want to have to keep doing this over and over again, especially if you had to do this like 3-4 times, it would get really annoying because then you'd have to substitute back into each one every time too and keep track of that negative, and if it was a constant that got pulled out and all of that business. Take a look at our answer. Do you see a pattern in there? Anything that jumps out at you? Say that really loud. There's a part of it. Yeah. What did you choose for u at the very beginning? X squared. X squared, 2x, 2, nothing. See that? Derivatives of that x squared. Okay. What did you choose as your dv right from the beginning? E to the x. Now in this case, what's the antiderivative of e to the x? Antiderivative, antiderivative, gone. Okay. So whatever you pick for as your original u and your original dv, you're having derivatives of that first thing each time, and you're having integrals of that other one each time, and then also positive, negative, positive, and then it will just continue if you have more terms. Okay. So as soon as the derivative or the integral is gone, we're done. Okay. So what we can do with this stuff is we can make a table. It's called tabular integration, where you can keep track of derivatives of u, integrals of v, and kind of match them up like this with the little plus minus going down the table. And then once you have it all, you can just string it all together. Okay? And it really streamlines this whole process so you don't have to keep thinking about this whole u dv over and over and over. And then if this integral, that's why the sign keeps changing each time too. Because every time you go through the process, you're taking a negative of whatever it was that you had. So it's going to keep changing the sign back and forth from positive to negative. Okay? So let's take a look at tabular. So let's see. So just by looking at this one, do you guys see how you would have to end up doing this process over and over again? I got x to the third. That would probably be your u, right? When you're starting? Because that one gets simpler each time as you take a derivative of it. But how many times do I have to take a derivative before I don't have an x in front of cosine? At least 2. Probably 3. So you would have to go through 3 sets. You get to something where you can actually do the integral at the end of it. I don't want to do that. because that's kind of that pattern we talked about that we noticed. So start with x to the third, and just start doing derivative on. So 3x squared, 6x, 6, 0. dv, we had cosine x, x, sine x, is the antiderivative of sine x. These guys are not getting any simpler. Getting to 0. And if we're multiplying things together, and the one side's eventually getting to 0, the whole thing is going to eventually be 0, right? Because it's 0 times whatever the heck you had on the other column, and it doesn't matter anymore. That these paired up, just because of the nature of how the form with each one of these. So at x, but it doesn't matter because it's 0, right? So we don't need to do that next part of that column, because it would end up being 0 times who cares? So we don't do it. And that whole plus minus thing happening too, okay? So the first one's always positive, okay, because there's no minus on. So those arrows are telling you what multiplies to what, and then just make sure you've got the appropriate sign going with that, and you just add all those things together when you're done, okay? And the next one, turn that to plus then, right? It's a minus next. And then we've got 6x and a negative sign x, but it's positive because of this negative, we're going to have a minus sign here. So minus 6x sine x. And then the last one, 6 and a cosine, but we got to do the minus with that as well, so it's minus 6 cosine. And then as always, okay, so this would be antiderivative of that, okay, using tabular integration to do it. So, does that make sense? How that works? Okay, I'm going to give you one more. I want you to practice with this, and then I think we'll be about out of time. So, or it'll be, well, we'll see. Tabular integration to calculate fourth e dx. This is one. So try it with the table instead. clicker? No. Oops. No, that's right. All right. Fourth e to the x minus 4x cubed. Now, like I said, I got one more I wanted to show you because these are weird. Notice about how we want to pick a u or a dv in such a way that when we do these repeated derivatives or repeated integrals, things are going to get simpler at least somewhere. What if derivatives or integrals of e to the x, they do nothing, right? Stays e to the x no matter what. Cosine x, best you're going to do is it's going to change to a sine, or maybe make it negative as you continue to go either way, okay? So, nothing there. There's a sneaky way to have to do. We can't do the tabular, though, because the tabular is just going to keep going, and never stop. Twice, but we can do it. You just have to kind of see this thing played out a little bit to see exactly what's going on. Yeah, and v, if this. Okay, so what we got, u times v, e to the x, sine x, minus the integral of v du, so e to the x, sine x, dx. Okay, great. So I swapped this integral for this one, which is no better, right? However, I do it one more time. Okay, come down here. We'll do e to the x sine x. Oops, I need my u is e to the x. And my dv is sine x dx. Oops, I forgot my x up there. So du e to the x dx. My v would be negative cosine x. So this one, u times v, negative e to the x cosine x minus the integral of v du. So since this is negative, actually we can turn this into a plus then. But then I've got e to the x cosine x. Okay, so I have an integral in there that I can't do yet. I'm going to take this, just like we did before, and I'm still going to stick it in for this. So I'm going to write out and see if you notice what's going on here. So we've got the original integral was the integral of e to the x cosine x dx. It's going to be equal to e to the x sine x, and then minus, right, because I got this minus sign, this. So it's going to be plus e to the x cosine x minus, if I distribute that negative, the integral e to the x cosine x dx. So this is where I'm at now. After I make about those integrals. There is that, but look at the integrals specifically. What do you notice about those two integrals? They're the same thing, right? Let's check. Like terms. They're exactly the same integral, so I can add. It's like the integral of the x cosine x is like a giant variable, and I'm just adding another one to the other side. Okay? Actually evaluating an integral, right? I used the fact that the integral I was trying to find popped up in the answer, so I just added a multiple of it over to the other side to answer. Right? It's done. Oh, except plus c. But yeah, okay. So if you get to the situation where you have your integral and your derivative, both of which not going anywhere, if you do it a couple of times, you might end up right back where you started, and that's actually a good thing, because then you can do this little trick. Okay? So I wanted to show you at least that, because that does happen. It is possible to get an answer with those. You just have to kind of stay the course and think about it that way. So tomorrow's an online day. I'll get your stuff up on course sites for you.